Thank you for joining us on Synthesis Workshop. In today's installment of our Advanced Organic Chemistry course, we're joined by Dr. Yael Ben-Tal. Yael has previously joined us to talk about her work on reaction kinetics of photoredox cross-couplings, so I'd also encourage you to check out that Research Spotlight episode when you have time. To quickly reintroduce Yael, she completed her bachelor's degree at the University of Auckland before coming to the University of Edinburgh, where she completed her doctoral work in the Lloyd-Jones group. She subsequently completed a postdoc in the group of Professor Marcel Utz at the University of Southampton before coming to the University of British Columbia, where she's currently a postdoc in the Hein group. Taking a look at where we are in the course, today we'll be continuing our Special Topics and New Technologies module, as Yael gives us an introduction to advanced NMR techniques. As a quick reminder, check out the rest of the talks in this course when you get a chance, and tell your lab mates about it if you found it useful. And with that, I'll hand it over to you, Yael.
Hi, and welcome to this video on solution-state NMR spectroscopy for organic chemists. Before we jump into the rest of the video, I just want to briefly stop and talk about what we will and what we won't be covering in the rest of this video. So we're going to start off with a very brief review of the principles underpinning how NMR spectroscopy works. We're then going to move on and start talking about various practical considerations that need to be thought about when recording NMR spectra. And finally, we're going to move on to talking about a varied array of different types of experiments that you can do beyond the basic 1D proton and carbon experiments that you're probably already familiar with. Now, because I assume people watching this video probably already know a little bit about NMR, one of the things we're not going to be talking about is things like the chemical shifts of different functional groups, J-couplings and splitting pattern multiplicities, and how we use all of those and integrals to be able to do structural assignment from basic 1D NMR spectra. On the flip side, we're also not going to go into very much detail at all about NMR theory. There's a lot of really interesting theory underpinning how NMR works, but we just don't have the time to talk about it here. Similarly, we're not going to have any discussion at all of the kind of radio frequency pulse sequences that mean that the experiments we talk about actually work. For more information about that, I recommend specifically the Timothy Claridge book that I've referred in the list of resources on the slide. All of these resources are things that I highly encourage you to look at if you want more information about all of the things we're not talking about in more detail. And I'll be flagging various resources as we go through this talk and at the end as well. And you should be able to find all of these in the description of the video. The final thing that we're not going to cover at all in this talk is solid-state NMR spectroscopy. Solid-state NMR is its own really interesting and additionally complex beast, and as organic chemists we tend to not need to use it very often. We just don't have time to cover it in any detail here. Again, if you're interested, there are lots of resources you can use to learn more about that. So, like electrons, nuclei have a property called spin, which we can think of essentially as being a magnetic moment with an angular momentum. Now, outside of a magnetic field, this magnetic moment points in any direction, but inside a magnetic field, it lines itself up in a number of orientations relative to this magnetic field. So, one way it can do so, the lowest energy state is aligned in the same direction as the magnetic field and precessing around it. Now, for a spin-half nuclei, like most of the nuclei relevant to organic chemists that we look at in NMR, there are two energy states it can have. It can precess in the same direction as the magnetic field, like we've shown here, or it can line up against the magnetic field, like here, and we call these the alpha and the beta states. Now, the alpha state is going to be lower in energy than the beta state, and the difference in energy between them is going to be a function of the magnetic field that we've put them into. It's also going to be relative to a constant called a gyromagnetic ratio, which is different for every type of nucleus we look at. Now, of course, normally we look at more than just one or two nuclei. We look at a whole population. And so all of the nuclei will be either in the lower or the higher energy state. And the amounts in each of them will, of course, be relative to this energy gap between them. To make our lives a lot easier, what we can then do is we can average out the magnetic moments of all the individual nuclei and look at what we call the bulk magnetization of the sample. And this will sit directly in the same direction as the magnetic field. Now, if we perturb this equilibrium with a radio frequency pulse, we can move it so that the magnetization is no longer sitting alongside the magnetic field, but instead perpendicular to it. And now it's going to precess around that field and return back to equilibrium. As it does so, it's going to induce a current inside a detector, and we can turn that current into a signal that we can then process to get the signal that we all recognize. Now, the energy gap between the alpha and the beta state from which we get the frequency that we look at in our signal is dependent on the magnetic field felt by the sample. But in a molecule, different nuclei are going to feel very slightly different magnetic fields because of shielding effects by the chemical environments around them. And they're going to have a very slightly different frequency from what they would have if they were exposed just to the magnetic field. This tends to be in the order of parts per million, and that's where we get the chemical shift scale that we're all very familiar with in ppm, parts per million. In addition, if you have multiple nuclei adjacent to each other in a molecule, the state of one of the nuclei is going to start affecting the state of the other one. And so you end up with splitting patterns that, again, we're all very familiar with seeing in our NMR spectra. Again, as I said before, I'm assuming that most people watching this video are familiar with analysis of coupling constants, and so I'm not going to talk about that in much more detail now, except to point out a couple of circumstances where you should be a little bit aware of what's happening. So for example, this spectrum here looks like a nice, very standard doublet of quartets. But actually, it's a doublet of triplets. It's just that the doublet and the triplet have the exact same J coupling constant. So it looks like a doublet of quartets. So this is just the kind of thing that it's worth keeping an eye on, and I just wanted to bring it up here briefly. Now that we've talked a little bit about how NMR spectroscopy works, I want to talk in a bit more detail about the kinds of instrumentation that we use to record NMR spectra. So most organic chemists, when you think of NMR, what you think of is what we call a high field NMR, which is a very, very big magnet so that we get the highest possible sensitivity. These are in some ways basically glorified thermoses. They're primarily composed of cryogens around an electromagnet, keeping it cool enough to generate a really strong magnetic field. In addition, in this magnet, what we tend to have are things that we call shim coils, which allow us to slightly adjust the homogeneity of the magnetic field to make sure it's as homogeneous as possible across our sample. Now, inside the magnet sits what we call the probe, which consists of the coils that transmit the radio frequency pulse that allows us to generate the NMR signal and receive the NMR signal back so we can then take it and turn it into a spectrum. Connected to the probe is something called a radio frequency preamplifier, which takes the signal that we're generating and amplifies it so that we can use it more effectively. And this all talks to something called a console, which is a big box, tends to be tucked away into the corner of the NMR labs. And these are the brains of the spectrometer. They contain all of the parts that let you regulate radio frequency transmission and detection, let you regulate all of the various bits of the instrument, and communicate over to the computer so that the user can talk to the spectrometer and tell it what to do. In addition to these high-field NMR instruments, something that's becoming more and more common these days is something called low-field or benchtop NMR, and you can see a photo of one up here. Now, these fundamentally work the same way as the high-field NMR instruments I was just talking about, except for they use much lower magnetic fields. This means that they don't need cryogens in order to keep them cool, and so you can fit all of this instrumentation that takes a small room to maintain and put them into a little box that can just sit on your bench and talk to your computer. Now, of course, one of the trade-offs of this is that you do tend to get lower sensitivity and lower signal to noise. So I want to very briefly talk about some of the aspects that affect sensitivity and noise in NMR. So initially, the first thing is just your concentration. The more sample you have, the more signal you'll have. It's also relative to the gyromagnetic ratio of the nuclei that you're looking at. So some nuclei are just intrinsically more sensitive than others. We tend to refer always back to protons or hydrogen atoms because they're the most sensitive nuclei we know. It's also proportional to your magnetic field, which is why generally if you're using one of those benchtop NMRs, you are going to need slightly more sample to get an equivalent level of signal. Finally, it's also proportional to the square root of how many scans we use. So generally, when we measure NMR experiments, we conduct the same experiment multiple times on a sample and we add up. the data from all of them. But this will only give you limited returns after a certain point. So now that we know a little bit about how the hardware looks, I want to talk a bit about the workflow that we have to go through in order to acquire an NMR spectrum. Now, the order of operations will vary slightly between different spectrometers, and often this can be done automatically. So in many cases, all you need to do is walk up, put your sample in, tell it what you want it to run, and walk away. But I think even if you're fortunate enough to be in an institution where all of this is done automatically for you, it's worth having an understanding of the steps that the spectrometer has to do before it can acquire a spectrum, if only so that you can troubleshoot afterwards. So the first step, of course, in recording an NMR spectra is you need to prepare your sample. Generally, a good rule of thumb for high-field NMR magnets is about 10 milligrams of sample and about 500 or 600 microliters of deuterated solvent inside an NMR tube. Once you've put your NMR tube in the magnet, the next step is locking on. A lock is basically when the spectrometer picks one frequency that it can detect and says, that frequency there, I know what it is, and I'm going to make sure it stays there the entire time. So typically this is often done off your deuterium signal from your deuterated solvent, but not always. And what this means is it makes sure that the magnetic field is consistent throughout your experiment and that you don't get any drift while you're running it. A lot of modern spectrometers also use that lock signal from your solvent to help set your chemical shift scale. For example, if I'm running an experiment in DCM, but I tell the spectrometer that I'm running it in chloroform, chances are it's still going to find some kind of signal and lock onto it, and the sample will still run, but then when I get my data back, I'll find out that all of my chemical shifts values are about 2 ppm off what I expected them to be. A lot of the time, this lock signal was also used to help the spectrometer with shimming, and we'll talk a bit more about what that is in a second. So once you've locked on, the next thing that needs to be done is tuning and matching the spectrometer. So tuning is telling the spectrometer what frequency you want to work at, because this will be very different depending on what nucleus you want to measure. Matching is basically making sure that we can get maximum signal at that frequency. So these graphs that you can see up here are basically graphs of frequency on your x-axis against signal attenuation on your y-axis. And we want to make sure we have as little signal attenuation as possible at the frequency that we're measuring. So that one on the top left is a good tune, because we've got the lowest attenuation at the frequency that we care about, but it's still quite a lot of attenuation, so it's not a particularly good match. On the right, we've got a good match, but not in the right spot, so it's not a very good tune. And finally, the middle bottom graph is something that's both a good tune and a good match. And the reason we talk about both of these at the same time is because they're not actually independent of each other. So generally you need to adjust one and then adjust the other and then adjust one and adjust them both together until you've got it optimized. So once we've done all of this, the next step is to shim the magnet. And shimming it is basically adjusting the homogeneity of the magnetic field so that it's completely homogeneous throughout the whole sample. Because if it's not homogeneous, every bit of the sample will be experiencing a slightly different magnetic field, and that will lead to broadening in your overall spectrum. Now this needs to be done for each individual sample, because things like how much solvent you've put in, what type of solvent you're using, what kind of molecule you're looking at will all very slightly affect the homogeneity of the magnetic field. And so here you can see the same sample before and after I've shimmed it, and you can see a massive difference in the quality of the spectra. So finally, what we need to do is we need to do what we call adjusting the receiver gain, which is basically playing around with the amplifier to make sure we get as much signal as possible out of our sample. So if we don't set it high enough, we just tend to not really get a signal at all. On the other hand, if you set it too high, you start bringing artifacts into your spectrum. So you want to make sure it's set to an optimum point where you're getting as much signal as possible without inducing these artifacts. So once we've done all of this, we can finally acquire our spectrum. We do this by hitting our sample with a train of radio frequency pulses, so either just one pulse or a series of them in sequence. And then we wait and we acquire our spectrum. And then often what we need to do, as I talked about before, is we need to wait some time and do it again and again to keep it, to increase the signal that we get. So overall, spectra will take you anywhere between seconds to hours to days to run, depending on what kind of experiment you're looking at. After we've acquired our data, we get it in the form of what we call an FID, a free induction decay. which is basically a bunch of frequencies all superimposed on top of each other. What we can then do is we can do what we call a Fourier transform onto it to pull out all of these individual frequencies and get out the more familiar type of spectrum that you're used to seeing. Now, there's a couple of different tricks that we can do with our data, both before and after we Fourier transform it, to change the way it looks a little bit and to optimize the kind of spectrum that we get. So the first thing that's done very routinely is something called zero filling. What this does is it basically takes the FID, and after we've stopped recording it, it very explicitly says this data point is 0. And we do this up to as many points as the data points that we have in the FID. And a lot of the time, this will have already been automatically done for you when you get your spectrum. And the effect of this is basically just increasing the data density up to a certain point. Something else that we can do is what we call apodization. So if you look at an FID, most of the data comes from the bits right at the beginning of it, and most of the noise comes from the bits right at the end. So what we can do is we can apply some kind of function onto our FID to say, look, we want you to value the stuff at the front more than the stuff at the end. So this has the effect of reducing the noise in our spectrum. But as you can see here, it also has the effect of broadening out our lines a lot. So it's always a trade-off. You're losing noise, but you might also be losing quite a bit of the fine structural information. Once we've Fourier transformed the data, sometimes there's a bit of processing that we need to do on the spectrum itself. So sometimes our peaks aren't all perfectly positive, and we need to apply what we call a phase correction onto it. Another thing that sometimes needs to be done, not so much with proton NMR usually, but often with other nuclei, is we need to apply a baseline correction to get rid of any background broadening in the spectra. So for example, the spectrum on screen here is a fluorine NMR, and the probe that I measured it off had some fluorine built into the probe. So every fluorine NMR that we ran would have this broad noise sitting in the background that we needed to get rid of. One really important aspect of NMR is that it's able to give us quantitative data, but we do need to be a bit careful about what we do and how we acquire our spectra to be able to make sure that it's quantitative. And it's not really a one-size-fits-all situation. So if you remember any kind of structural analysis that you do, one of the main tenets of it is that if you've got, say, an integral pattern of 1:1:2, that means that you've got one proton in one chemical environment, one proton in another chemical environment, two protons in a third chemical environment. But generally, you don't actually get 1:1:2 integrals, right? You get 0.9 is to 1.1 is to 1.95. So you get approximate numbers. And that's because the default experiments on most spectrometers are set to good enough quantitation. They're giving you numbers that will be good enough for most purposes. But if you want really accurate integrals, you tend to need a slightly more active hand in setting your parameters to make sure that you can get proper quantitation. And to understand what these parameters are, why that is, and how we know how to set the parameters properly, we need to jump back and have a little bit of another look at NMR theory. So if you remember, generally we consider our magnetization aligned with the magnetic field. This is the equilibrium situation. We then record a spectrum by perturbing the equilibrium. We hit it with a radio frequency, and now the magnetization is perpendicular to our external magnetic field. Over time, that magnetization is slowly going to relax back to the equilibrium state until finally it's restored completely. And it turns out that we can figure out how much of our magnetization is back in the direction of the magnetic field using this formula here. So it's an exponential function of both the time we've let it to relax and this constant we call T1, which is a time constant, but normally we call it the relaxation time of the system. And it turns out that in order to get your magnetization completely restored to the equilibrium situation, or close enough to completely restored that it doesn't make a difference, we need to wait for at least 5 times that T1 value before we can take another spectrum. And this has really important consequences for quantitating NMR. So what you can see here is 2 different spectra that I took, where both of them were taken with the same number of scans. One of them was taken not waiting very much time at all between scans. The other was taken waiting for 5 times the value of the longer T1 in the system between the scans. And you can see, first of all, the signal intensity is a lot higher in the second one. And second of all, you can see that this is the exact same sample, but the integral ratios have really dramatically flipped here. This is because I'm not giving enough time for both the systems to fully recover. And so what ends up happening is my integral for my peak on my left is artificially inflated relative to that of the peak on the right. So if you want to quantify integrals properly, you need to make sure that you wait for at least 5 times the T1 between every scan in your experiments. And in order to be able to make sure you're waiting long enough, you need to have an idea of what the T1 value of the molecule you're quantifying is. So how do we do that? There's lots of different ways to measure the T1, and there's quite a lot of references down below here that you can use for more information. But the most common method is what we call the inversion recovery experiment. So in this experiment, we basically completely invert our signal, so it's giving us a negative peak like you see in that front one of the array that I've shown here. And then we record another spectrum, waiting a certain amount of time. So if we don't wait any time at all, we see that inverted peak. If we change the amount of time we wait between recording the spectrum, the peak grows in until finally we get the positive peak that we'd normally expect. So we can take the integrals of all of these peaks and plot them on a graph, like so, and then we can fit an equation to this data and pull out the T1 value. And a lot of this can be automatically done by a lot of NMR software. So you can run your T1 measurement and it can just spit out the number for you. Although it's always worth keeping an eye and making sure that the fitting is actually done properly. Something else that we can often see in our NMR spectra is line broadening. Now this can come from a variety of different causes. So one of them could just be issues with the acquisition or with the processing. So for example, the magnet hasn't shimmed properly, or the person who used the spectrometer before you set a really large exponential correction on their data and accidentally set it so that it would go through to everyone else's data. So this is just something that's always worth checking if you can. Another common cause of line broadening is something like sample inhomogeneity. So say you've got solid precipitating out while your NMR tube is sitting in the magnet, you've got phase splitting. It's always worth just having a quick visual check of your NMR tube if you have access to it. Another thing that can cause line broadening is the presence of paramagnetic species in your solution. For organic chemists, this will tend to come up if we're doing transition metal catalyzed reactions. Sometimes the paramagnetic species just itself will become very broad, sometimes everything in solution will become broadened. The final cause for potential line broadening in your spectrum is chemical exchange. So if you've got two species in solution that are in chemical exchange with each other, if the exchange rate is really slow, you see two nice well-resolved peaks. If the exchange rate is really fast, you see one nice well-resolved peak. But in the middle, when the rate of exchange is about the same as the timescale of NMR, you can see quite significant line broadening. The nice thing about this is that if we can change that rate of exchange, we can change what the spectrum looks like. And we can often do this just by changing the temperature that our sample is being measured at. You can see this when you've got multiple species in solution, but often you can also see it when you've got one species. So for example here, the 6-membered ring here happens to be exchanging between the two different chair conformers at about the rate of the NMR timescale, and you end up with this really, really broad peaks in your proton. So what you can't see here is that the R group of the nitrogen, all of the peaks in the proton are very well resolved and very sharp, and it's just this ring here that's broadened out. Something else that's worth considering as an organic chemist doing NMR is that proton and carbon aren't the only two nuclei that we can NMR. There's quite a lot of different NMR active nuclei all around the periodic table with various degrees of sensitivity and use. And I've just tabulated here a couple of the more useful ones for NMR chemists. So as well as proton, we can also look at deuterium NMR, and in fact it's that deuterium signal in deuterated solvent that we tend to use as our lock signal that we were talking about earlier. We can do boron NMR. People tend to do boron 11, but you can also do boron 10. Things to remember about boron is it's a quadrupolar nuclei, which means that it has a spin that's greater than half. So it will tend to be broader than the other ones. You can also do nitrogen NMR, though it's so insensitive that I would not recommend it except some 2D NMR instances. More useful are the three at the bottom, so fluorine, silicon, and phosphorus. They're all spin half, so they behave pretty much like the carbon and the proton you're more familiar with. Fluorine in particular is very naturally abundant and almost as sensitive as proton. with a much wider chemical shift range. So if you've got a fluorine in your molecule, it's very much worth looking into doing some fluorine NMR on it. The other thing that's worth remembering in all of these cases is the couplings between these heteroatoms and whatever nucleus you're measuring. So in proton NMR, phosphorus couplings to protons tend to be really big. So what might look like two singlets is actually a phosphorus coupled doublet. Similarly, in your carbon NMR, we tend to run carbon decoupled from the protons, but we're not decoupling it from any other type of nuclei. So if you've got phosphorus or fluorine in your molecule bonded to your carbon, you're still going to see the induced splittings in your carbon NMR, even though you're decoupling it from proton. And on a similar note, I just briefly want to talk about the use of isotopes in NMR. So the first thing that's worth being aware of is that there's something called the NMR isotope shift. So the chemical shift of something is very slightly different depending on if it's bonded to one isotope or a different isotope. And we can see that really clearly in the carbon NMR of deuterated chloroform. So we can see the triplet pattern that we've got from coupling between the deuterium and the carbon. Remember, deuterium has a spin of 1, not half, and so it will have a triplet when it's coupling to the carbon. But if you look closer to the baseline, you can see this fourth little peak down here. And this peak comes from the residual non-deuterated chloroform in solution. It's only a singlet because we are proton decoupling here, but the fact that we can see it at all indicates that it's shifted from the chemical shift of the deuterated chloroform. And you can see this anywhere where you've got labeled compounds. The other, of course, thing about using isotopes in NMR is that the most common place where we use isotopes tend to be in the use of deuterated solvent. We routinely will run our NMRs in deuterated solvent, and there's a couple different reasons why we do this. So the first one is to use as the lock signal, as we've talked about a little bit before. The other thing is to stop the proton NMR from being completely saturated by your solvent peak. So you deuterate it so that you don't see a giant solvent peak and you can actually see the rest of your spectrum. But of course, we don't necessarily need a lock signal if we're only running a spectrum for a couple of minutes. Or if, like in many benchtop NMRs, we're actually locking onto something that isn't the deuterated signal. And in terms of the detector saturation, that's not really a problem if we're looking at a nuclei that isn't proton. And if we are looking at proton, we can still often overcome it with a type of experiment known as solvent suppression. So you can see here, I've got two spectra. The top one is just my normal proton with a giant water peak in it. The second one is the proton NMR with water suppression. You can see that I've really gotten rid of most of that water peak, and I can much more clearly see the rest of the spectrum. And in fact, depending on how much effort you want to put into optimizing your solvent suppression parameters for a particular experiment, you can get rid of your peak to greater or to lesser extents. This particular spectrum was taken with fairly little effort. So the moral of the story is that you don't always need deuterated solvent, but of course talk to your lab manager. Different lab facilities have different rules about what they prefer you to do. So now we're getting to the final part of the video, where I'm going to talk about a variety of different NMR experiments and methods beyond the simple 1D proton and carbon experiments that you've probably all seen before. But first we're going to talk about something that's presumably very familiar to most of you, and that's decoupling, because most of the carbon NMR that we see have actually been decoupled from the protons in order to increase the sensitivity. So here you can see a carbon NMR in black that's not decoupled, and in grey it is decoupled, and you can see how much the sensitivity of our signal increases just by getting rid of all of those coupling patterns. But actually that increase isn't just from not losing your multiplets to the baseline. Some methods of decoupling also give an additional sensitivity boost, and that's one of the reasons that we tend to decouple. Now, when you think of decoupling, you tend to think about decoupling one nucleus from another. But we can also do what we call pure shift NMR, which really is just homonuclear decoupling. And that's decoupling all of the protons in solution from each other. So you can take something like this with a very, very complicated series of multiplets, and you can get rid of all of those multiplets and just have one peak per chemical environment in that molecule. Now, of course, what this means is that we lose quite a bit of the structural information that makes NMR so useful. But there can be instances where being able to see the individual chemical environments cleanly resolved from each other can be quite useful. The next technique I'm going to talk about is still a 1D NMR technique, and it's something that we call polarization transfer. So if you recall from our earlier discussion, the sensitivity of your NMR is dependent on the gyromagnetic ratio of your observed nucleus. So some nuclei are just inherently going to be more sensitive than others. Now, what polarization transfer does as a technique is it takes one more sensitive nuclei, usually proton, and transfers some of that sensitivity to an adjacent less sensitive nuclei, often but not always carbon. So what we do is we essentially excite on the proton, we transfer that excitation onto our X nuclei, and then we measure on X. So there are a few different related NMR techniques that all work on the polarization transfer principle. One of the original ones is called INEPT, insensitive nuclei enhanced by polarization transfer. And what this basically does is it increases the sensitivity of your sample, but it doesn't do so uniformly. So you can see in this little cartoon, the sensitivity of the signal that doesn't have any attached protons is not enhanced in the same way that the other ones are. You're probably going to be slightly more familiar with a technique called DEPT, which stands for distortionless enhancement by polarization transfer. Now, this is a similar experiment, but it turns out that a side effect of DEPT is that we can vary one parameter in the pulse sequence. That's what the numbers come from in different DEPT experiments. DEPT 45, DEPT 90, and DEPT 135. Those numbers are in reference to that one parameter that we change. And by changing that parameter, we can make it so that different kinds of chemical environment react differently to the polarization transfer. So in DEPT 45, we can't see something that doesn't have a proton attached to it at all, and all of the other ones will just be positive. In DEPT 90, the only thing we can see is carbons with only one proton attached to them. And in DEPT 135, we invert the carbons with two protons, can't see carbons with no protons, and have a positive peak for the CHs and the CH3s. So because of this additional ability to distinguish different carbons, DEPT tends to be a lot more common than INEPT for carbon these days, but INEPT is still used a lot, for example, in silicon NMR. Something else that we can do is we can selectively excite parts of the spectrum. So we can take a spectrum like this one here and we can say, hey, I only want to look at this peak here, and we can make it so that we only look at that peak there. Now this seems like it's not super useful in and of itself, but when we combine this technique with various other NMR experiments, we can get something really powerful. And a kind of similar principle is behind the solvent suppression that we were talking about earlier in this video. One thing that uses the effect that we can selectively excite different parts of the spectrum to great effect is a technique called saturation transfer difference NMR, which is used a lot in drug binding studies. So the way this works is that you have a solution that's got your protein and your ligand, or the thing that you're binding and the thing that you're binding to. And the thing that you're binding tends to be in much larger amounts than the thing that you're binding to. And they exist in equilibrium with each other. So your free and your bound ligand exist in equilibrium. And you can take a proton of that and you'll see mostly your ligand because it's in greater concentration, but you'll see everything in your spectrum. What you can then do is you can selectively excite just the protein, and that excitation will be transferred through the chemical bond over to the bound ligand, which can then detach and go free into solution. What we then do is we take another spectrum and we take the difference between that spectrum and the pure proton spectrum. And what this does is it only highlights the bits that are most involved in the binding. And so this can be a really important tool for understanding how molecules are binding into biological systems, although this of course is not the only application for STD NMR. The final class of NMR experiments that we're going to talk about in this video are a very diverse range of NMR experiments called 2D NMR that are incredibly powerful in terms of the structural information that they can give us about molecules. Most of these experiments work on the same basic principle, which is that we take a bunch of different spectra with variable delays as part of the pulse sequence that we're not going to talk about in any detail. And what that means is that we end up with a series of spectra that look something like this. We can take the integrals of all of those peak, and we can generate something that looks a little bit like the FID that we get from standard NMR experiments. We can Fourier transform that in just the same way, and what we end up with is the general structure of a 2D NMR spectra, where we have what we call a direct dimension, which is a spectra that we measure normally, and we have the indirect dimension, which are the spectra that we generate in the way I've just talked about. So there are a couple of 2D NMR experiments that don't work quite like this, and we'll talk about them later. But generally, the structure of these experiments is we've got two spectra at right angles to each other with a contour plot between them, and it's these cross peaks in the contour plot that can give us lots of really useful information about the way those two spectra relate to each other. So the simplest type of 2D NMR is called COSY, which stands for correlation spectroscopy. And this is correlation between two identical proton spectra. And you can see this cartoon here shows kind of what a COSY looks like. So there are two distinct parts to a COSY spectra. The first is what we call the diagonal peaks, which I've just highlighted here in gray. And these are basically showing that the same peaks in each spectra are the same peaks in each spectra. The ones in black are slightly more interesting. These are the off-diagonal peaks, and this is where COSY has its real power, because these peaks show us which peaks in your proton spectrum are coupled to which other peaks in your proton spectra. So here, B and C are coupled to each other, B and A are coupled to each other, but A and C aren't coupled to each other. And from this information, we can start figuring out what the architecture of this molecule looks like. Now I want to talk a little bit about a real-world example for all of these 2D NMR spectra. So we're going to look at this molecule lysibabarine A, which was identified in 2021. And these are the spectra that were used by the group that identified the structure of this. So this is the COSY that they took. And we can see we've got this little square corner down the middle here, which shows us the coupling between those protons 6 and 7, highlighted in yellow. And if we zoom into the rest of the COSY spectrum, we start seeing more and more correlations at play. So we can start seeing the couplings on this proton 14 here, and we can see that they're both on the same carbon, and we'll look at that more when we look at the proton-carbon 2D spectra in a second. We can then see how they're both coupled to the protons on 15. We can see how that in turn is coupled to the protons on 16 and 17, and we can start building up an order of the connectivity of the architecture in this molecule. We can also look at the other couplings in the COSY, and we can similarly start looking at the connectivity of the molecule. Now, there's also an extension to COSY called TOCSY, which stands for Total Correlation Spectroscopy. And in this case, it brings in all of the correlations within a chemical network. So in this particular fake example here, A and C aren't directly coupled to each other, but A and C are in the same chemical shift network, and so we would see that peak in the TOCSY, so that the overall spectrum would look something like this. On top of having correlations between two identical spectra, we can start looking at correlations between different nuclei. So the most common version of this is what we call HSQC, which stands for Heteronuclear Single Quantum Coherence Spectroscopy. And here we see the peak in your proton spectrum and the corresponding peak in your carbon spectrum, or your X spectrum. To be clear, you don't actually need to just do HSQC between a proton and a carbon. You can do it between a proton and a nitrogen. Going back to the COSY, you can do that between two fluorines just as much as you could do it between two protons. And so here we can see that proton C is sitting on carbon Z, D and B are both sitting on the same carbon, which is X, and A is sitting on W, and Y and V don't have anything sitting on them. Looking at our lysibabarine A example, we can use this to correlate all of the proton spectra with all of the carbon spectra, which is really helpful for making the proper structural assignments of this molecule. So we can see here that proton that's sitting on carbon 15 versus the one over here that's sitting on 16. And we can see that on 17 there are two distinct signals. And I'm not going to go through the entire rest of the molecule, but a similar technique lets you associate which proton are associated with which carbon. And later on during the structural assignment, we can assign exactly which one is which. And part of the way in which this can be done is using a separate 2D experiment called HMBC, which stands for Heteronuclear Multiple Bond Correlation. So what we're looking at here is another cartoon where in the dashed circles is what the HSQC we looked at earlier would look like for this molecule. Now the HMBC doesn't actually show those, so really it would look something like this. But in reality, we don't just see carbons that are 2 bonds away from the protons. We see carbons that are 2 and 3 and sometimes even 4 bonds away. So when we add in the 3J couplings, we get a spectrum that looks something like this. And this was used again in the case of lysibabarine A in order to properly assign the molecule. So you can see here, we can see the connectivity network of that aromatic ring. Zooming in again, we're starting to be able to see this connectivity network down here and the connectivity network up here. And we can kind of see the spots where those networks overlay via carbon-12. And what was really interesting in this particular case is they were even able to see 4 bond correlations in one particular case here, which really helped them pin down the exact structure of the molecule. A slightly different variation on 2D NMR is what we call NOESY. I'm also going to in a second talk about ROESY and XY, which are some variations on similar concepts. So NOESY stands for Nuclear Overhauser Effect Spectroscopy, and ROESY is Rotating Frame Overhauser Effect Spectroscopy. And both of these essentially use the same concept in slightly different post sequences, but we can consider them being very similar to each other. All of the 2D NMR we've looked at before is looking at through bond interactions with each other. But NOESY is looking at through space interactions. So for example, on a protein like this, these two protons could be tens of bonds away from each other, but they're right next to each other in space. So if we ran a COSY, we wouldn't see any kind of correlation between them, but on the ROESY or the NOESY, we very much see a crosspeak. I also want to very briefly talk about a fairly distinct type of spectroscopy called exchange spectroscopy, which lets you monitor chemical exchange. Now I'm bringing this up at the same time as ROESY and NOESY because actually it's the same experiment. We change some parameters, but the fundamental sequence of radio frequency pulses that we put into the sample is the same in both, though often our parameters need to be changed a bit. And so when you're trying to do one experiment, sometimes maybe you'll spot the other one as well. So the way these are structured is like COSY, it's a proton-proton correlation technique. You've got your cross peaks, and now you see correlations between things that are connected in space. So again, this is really useful to help you assign stereochemistry. And we can see this again in the case of lysobarbarine A, where I've included the 3D structure this time of the molecule for clarity. This was pulled straight out of the paper, so they've got all of the NOEs that they observed already drawn on in pink arrows, but I just want to highlight a few ourselves. So you can see here the coupling between H11, so that proton on the aldehyde, to the proton at 4 and at 6. You can also see here the correlations between 14B but not 14A and the proton at 16. And that's telling you what the stereochemistry is like at that center there, especially when you combine it with the interactions between other parts of the molecule. This is also an example of an XY spectrum. So here we have a bunch of species in solution and they're all in chemical exchange with each other. And what we can see is that these two peaks here, we can see clearly that they're exchanging with each other, as are these two peaks here. The final type of 2D NMR spectroscopy that I want to talk about is something that we call DOSY, which stands for diffusion ordered spectroscopy. Now this spectrum is a little different from the other 2Ds we've talked about before. And this is an example of a technique that's used more broadly in NMR, and that's called applying a magnetic field gradient. So we've talked a lot about how we really want the magnetic field across our sample to be completely homogeneous. But if we make it inhomogeneous and control the inhomogeneity ourselves a known amount, it turns out we can do lots of really interesting things on the sample. And DOSY is the most major example, but there are lots of other techniques that also use this kind of gradient approach. So if we apply a gradient of a magnetic field strength along our sample, every vertical part of that sample is going to have a very slightly different frequency. So we can tag positions inside the NMR tube. And by doing this, what we can do is we can generate what we call a DOSY spectrum, which is like a normal 2D, except for your second axis, instead of having a second frequency graph there, like in all of the other cases, we have a measure of the diffusion coefficient of each of the peaks. So in this particular cartoon example, peaks A and B have the same diffusion coefficient. C has a much larger diffusion coefficient, and D is somewhat in the middle. And that would suggest that these are 3 distinct molecules. So we can use this a number of different ways, and one of them is just being able to separate mixtures out by NMR without actually having to do any physical separation ourselves. Another example of the use of DOSY is in this particular case here, which has been used to demonstrate formation of an ion pair. So we can see the DOSY spectra of these 3 samples all mixed together, and we can see that when another component is added, one of those species dramatically changes in diffusion coefficient, showing that it must be forming associations within different molecule in solution. So we're now coming to the end of our very rapid introduction to advanced NMR for organic chemists. I hope you found this video useful. We really did only manage to scratch the surface of most of the things we talked about. So if you're interested in delving a little deeper, on the left we have a series of recommended textbooks. And on the bottom left, there are a couple of links to different YouTube videos that are quite useful in terms of understanding a little bit more about NMR theory. On the right, you can see several different resources to several different blogs that have quite a lot of useful information, structural assignment problem sets, a few different papers with different relevant bits of information. And of course, all of these will be linked in the description of the video. So thank you very much for watching. I really hope you found this useful. And thank you again to Matt for inviting me to talk.
Thank you for watching this talk, and thank you to Yael for a very instructive talk on NMR. Tune in for our next installment of this course as we learn about phosphorus.